Learning outcome 2-2, convolution of two continuous time signals, examples with a function with constant functional values. We've introduced to you the convolution integral and the convolution sum. Now we're going to work through a problem about how to use this for problems. These problems are typical ones we start with, where we're talking about something with a constant value, limited in time. This will give you the general idea about how to actually use this integral to solve a problem. In this example, we consider our x of t, which is time limited between time 0 and time 3. It has an amplitude of 1. Our h of t is time limited between time 0 and time 1 with an amplitude of 2. We have equations that define them and pictures that define them. You always want to draw out the picture and the equation and use both together to solve the problem. While we have these equations, the integral has an x of tau and an h of t minus tau. Neither of these are those equations that are in your integral. So we have to do something to these equations to get the ones in the integral. X needs to have an argument of tau. We can do that. Change your t's into taus. Look what I did. I just changed all the t's into tau in both the equation, and that just changes it to a tau in the picture. H of tau changed likewise. But we don't need an h of tau, we need an h of t minus tau. How do we get an h of t minus tau? If in order to get an h of tau, we replaced all of our t's with taus, what do we do if we're trying to get an h of t minus tau? Replace all the t's with t minus tau. Please do this and simplify your algebra. And what happens to your picture when you do that also? Please pause the video and work this out. When you replace all your t's with t minus tau, your t's become a t minus tau. We can then move the t to the other side, so subtract t from all the terms. Now we have all these minus signs. Multiply through by -1, and note that that's going to flip the direction of your inequalities. For your picture, you don't see very much if we're flipping things, so I'm going to label the time 0 with green and the time 1 with purple dashed. H of t minus tau, because we have a minus tau, we're looking at the variable tau, is going to flip our graph around, which is only visible when I've labeled these with the green where it was originally 0 and the purple where it was originally 1. How do we know what these time units are? If the argument was 0, which is where it was green, that's when the argument, t minus tau, is 0. Algebraically, solve for tau, wind up with tau as t. So where we had initially time 0, which is our green side of this pulse, we now have tau is equal to t. When our initial time argument was 1, our new time argument, t minus tau, will be 1 when our variable, tau, is equal to t minus 1. So we're going to label this as a t minus 1. When we want to solve for this, we need to consider all the different times t and run that integral for all the different t's that are possible. So let's start with time t is negative infinity. When t is negative infinity, this square pulse is to the left of this square pulse. And this will be totally to the left and not have any overlap so long as this spot here, t, is to the left of this spot here, 1, or t is less than 1. The product of these two functions is now 0, and therefore the integral of them is also 0. But this is only 0 when t is less than 1, when these two do not overlap. Let's increase t such that they now overlap a little bit. T is now to the right of 1, so therefore t is bigger than 1. But we're going to have it partially overlapping so long as t minus 1 is to the left of 1, which is our other condition for when this is going to hold. As soon as t minus 1 gets bigger than 1, we have a different situation. Combining these two conditions together gives us time from 1 to 2. The integral which we will write has our functional values, which are the 1 and the 2, inside here, and we're integrating between 1 and t, because that's where we have these values 1 and 2. At all other times, we've got either 0 times 0, 0 times 2, 0 times 1, or 0 times 0. And all of that just doesn't matter. Those will all be 0. Only when we're integrating between tau of 1 and tau of t in this region will we have non-zero values. When we do the integration, we get 2 tau. We can then substitute our values in 2t minus 2. Notice that this is our y of t, which is a function of t. We at least know there's a chance we did it right. If you have any taus in your output, you know you did it wrong. Keep moving our pulse to the right to greater values of t. Now, this trailing edge, t minus 1, is to the right of this leading edge of the shorter pulse. So t minus 1 is greater than 1, or t is greater than 2. But we want to consider this case only before t reaches 3, so when t is less than 3. Combining these two together says that this picture, this case, is valid when t is between times 2 and 3. What's our integral? Again, we've got the functional values of 1 and 2, but these are only those values are only valid between time -1 and t. Everywhere else we've got zeros multiplied by something. Work out this integral, and it's 2. This is a constant, it has no t's in it. No taus, which is good, but also no t's. This makes sense because this has a lot of ability to move for a bunch of different t values and not change the product, what we wind up with. If we keep increasing our t, now our tall pulse is slightly off and beyond our short pulse. So again, we have partial overlap. We'll have this partial overlap whenever t minus 1 is to the left of 3, therefore t is less than 4. But also it has to be the case that t is to the right of 3, therefore t is greater than 3. Combining these, t is between 3 and 4. What's our convolution integral? The values of our amplitudes are 1 and 2. Those have not changed. But we're only going to integrate in this region from t minus 1 to 3. Do your integration, substitute in. Note that again it's a function of t, no taus remain. Keep moving your pulse to the right. And they no longer overlap if t minus 1 is to the right of 3. We get this inequality, which is equivalent to t greater than 4. Because there's no overlap, we don't need to do the integral. We know that our y of t is 0. We have all 5 cases. We want to summarize them and put them all together. Make sure you've been writing the information down, each one. You need to have a y of t. You have a time when it's valid. We didn't have any equalities in our limits when we were doing things before. We can add those here at this point. Check that your limits all are adjacent to each other. We end with a 1, we start with a 1, we end with a 2, we start with a 2. Make sure you do this at the end and not before, because if you're just guessing this is going to be the case, you might have made a mistake and not noticed it. Check your answer afterwards rather than using this fact when you're doing the earlier calculation. Our final answer is after all the integration. We put our final answer together with each of the 5 cases and when each one is valid. Sometimes a picture is required. Here's what it looks like for this particular one. 0, linearly increasing, constant, linearly decreasing, 0. Also note that we have continuity of amplitude at each of these boundaries. That's another good check to see if you did it right. It doesn't guarantee that you did, but if you do not have continuity, you know you did it wrong. Try this problem out by yourself without this video and see if you can get the same results at the end.